2023. I'm Manish from AppSecEngineer, and today I'm joined once more by Ganga Sumanth, Associate Security Engineer at V45. He's the guy who's created most of the brand new Golang challenges we just released, and he's also one of the trainers on the upcoming Google Cloud Learning Path we'll be releasing very soon. It's going to be a huge addition to our library, and we can't wait for you to try it out. But for today's live stream, Ganga will be talking to you about Zero Trust Authentication. He'll be demonstrating some examples using Golang applications, but these techniques will be applicable on pretty much any other tech stack. I'll not take up any more of your time though, so over to you, Ganga.
Well, hi everyone. Thanks for that amazing introduction. Um, Let me just dive right in, I suppose. Give me a second. Okay. So, zero trust authentication paradigms. Well, that's a mouthful. But I assure you, that's the longest sentence we'll probably be saying in today's live stream. But what is zero trust authentication, and why are we even talking about something like this? If you've noticed, this is one of the buzzwords of today's world, and we can't seem to stop hearing it everywhere we turn. Um, but what does it even mean? Why are we even talking about it now? And have we never done this before? Well, in this session, I want to talk about that in a little more detail, and let's get going. So let's put everything on the table right now. What are we going to talk about today? First of all, I want to talk about what ZTA is, or what Zero Trust Authentication architecture talks about. I want to give you a good real-time, real-world example, so you will be able to understand how it relates in the physical world as well as in the cybersecurity world. And I want to talk about the authentication paradigms available to us. And then I will be talking about two different methods of authentication that we can use to they are two different ways to do this thing, to do authentication. And they will allow us to contrast the details between the two. And you will walk away with more details than you had before. Okay. So let's start off with zero trust architecture as it is. So, what is zero trust architecture, and what is it anyway? Like, why did we get here? Well, traditionally speaking, our networks were limited to physical spaces. Meaning, if you go way back to the ARPANET days, you had physical buildings wherein you would have your network defined only within that boundary. So if you wanted access to a computer, you would have to be physically present in the location. You would have various modes of authentication to get in. Perhaps you would have to be a student of a particular university, or you would have to be a worker or an employee at an organization to get access to these computers. So in case something were to happen on those devices, you would be held responsible immediately, because the physical location and the person who was using that device at the same time were readily available. Uh, these were metrics that could be accessed with very little difficulty. But something has changed since then. Our servers, which used to be in centralized locations, have given us so much. Like right now, or maybe about 5 years ago, we would have multitudes of devices that were connecting to singular servers. You would have all your mobile devices, all your desktops, all of them would lead back to a singular server that was located in some physical location. However, that has seen a massive change. The internet, on as we know it on the mobile side of things, has remained as is. Our smartphones have gotten smarter. We've got more devices in the house, but by and large, that has not changed as much as the other side of the spectrum, wherein the cloud-based computing has brought us something completely different. We are now looking at load balancers that can ensure all of your traffic is being distributed across a variety of websites and a variety of servers that are readily available and are always serving what you require, your computing power, maybe you need more memory, maybe you need more data storage, maybe you need analytics. All of these are going to happen as small microservices that are deployed across the cloud in small compute instances. Today is the day of ephemeral functions, of serverless computing. These truly are the new norm. So, on in this perspective, or in this new light, zero trust is an information security concept that is focused on the idea that organizations should not automatically trust any entity. We do not have any evidence that this person is who they say they are, or entity is even bigger than that. We're talking about every device on your network, every human being on your network, and the network itself. So perhaps one of the most iconic lines that I keep hearing when I was researching zero trust was the idea that treat everything to be hostile, treat the network to be hostile. And if you follow this perspective or this idea, then everything that you're designing from this point forwards is going to assume that the previous link in the chain is also somewhat suspicious, is also broken. So how would you go about doing this? Well, as an organization, you should be verifying every single access request, regardless of where it is coming from. Even if it is within your own organization, even if it is supposed to be on a server that you have complete rights over, or you know where it is, you should still be looking at it as a suspect in your network. Okay, that was a bit of talk, but let's see if we can bring this idea to be understood even better than that. Well, this is an interesting real world parallel that I could think about. So imagine the internet or the network to be an amusement park. And to be honest, this is not an entirely new concept. The internet at its base has been built on the concept of trying to hold private conversations in a public setting. You're trying to connect, you as a client are trying to connect to a public server, and you're trying to hold a conversation with it that you expect is to be only to be held between the two of you. However, every point in the network that you have to follow to get to that point is also publicly available. It is not just you and them, as in the client and the server. This is not a completely private conversation. However, to ensure that that is the case, there are various layers of security and various layers of encryption that are happening to ensure that this happens. But how do we do that in a world where you no longer know if the server itself is going to be one single entity? We don't know if the client is one single entity anymore. But anyway, let's talk about why I think this is a good parallel. So, in an amusement park, you have various control access points, meaning you will have one single entrance and one single exit. And at this very point, this bottleneck, if you will be ensuring that everybody entering the space has some form of authentication. So you will probably ask them to buy a ticket, and you'll give them a wristband. In a very similar fashion, if you were to port that principle over to your networking world or your security world, you would want to authenticate people with various layers of authentication. So you would use something like multi-factor authentication, and that wristband is then going to serve as that single point of sign, or SSO. You can also ensure that you have context-based authentication. So once they've entered the space, you still want to know if they have paid for a like the super luxury rides, or if they've managed to like fast track themselves. Those are also some things that you can use to give them layers of authorization once they've entered the space. And additional barriers around high risk assets. Okay, so this is an interesting one. So let us say your user has already entered your system, your network, but you want to ensure that they are only going to stay within the small piece of the small play area that you've defined for them. You only want them to access the rights, and you don't want them to go into the administrative division where you have your security cameras, or you don't want to go into them to go into generator rooms or into the points, basically places where they should not be. So how would you do such a thing? Well, there you have IAM, or identity access management. You have RBAC, which is role based access control. You have adaptive security, which ensures that if a particular user is supposed to be in a space at the given moment of time, you try to build strategies to ensure that they are in the space where they're supposed to be. If there is if there is any evidence to suggest that they have walked out of the bounds that they were supposed to be in, you deny their request from that point forwards. Next, you have pervasive monitoring tools like cameras and motion sensors all across your amusement park. Similarly, in our security context, we have continuous logging. Every single action that you perform within your system is going to be logged, and those logs are then enriched, and then we're going to be performing analytics on top of that to ensure that your system is performing as intended. And you're also going to be looking at the activity of the user itself, and if that is following a particular trend, then you can use that as a basis uh, for figuring out what could be suspicious activity. Finally, active response tools like guards and on-demand barriers. Well, in our case, that would be we would have certificates that are issued to the client and to the server. In any case, we realize that our hardware has been compromised, then that certificate can also be revoked using something like an OCCP, or which is an online certificate status protocol, that allows the compromised certificates to be revoked from the list of authorized certificates. Suspicious activity can also be flagged, and that user can be kicked out of the system or the network very quickly. Finally, recovery measures could be like, in this case, we're talking about tracking device and insurance. A good tracking device example could be, if you want to make sure that nobody is phishing your login page, you could put a small web bug on it. And in case you see suspicious activity on it, you could simply stop them. The bug would tell you every time that page has been replicated somewhere else. Then you would understand that that particular target is trying to pull your data, and maybe they will use it for um, bad purposes later on. Okay, moving forward. So, what is authentication? Like, why are we even talking about this? Or like, let us break it down into the most fundamental parts of this concept. Authentication is all about finding out who your user is, or who your client is, or who your server happens to be. In the perspective of zero trust, every single entity that we have within network has to prove its identity. And I want to talk about three different ways that we can do this. We have keys to your house, we have your Aadhaar card, and we have your debit or credit card. And the reason I've chosen these three items is because the keys are a physical device that you have access to, so you possess them. Your Aadhaar card is something that has uh, further evidence, like it has your biometric your scans, like it has your fingerprints, it has your retinas, or certain details that are extremely uh, pertinent only to you. And your debit or credit card, even though it contains your name and details, it can be used by anyone. If they have access to your details, if they know your PIN card number, they can also use it. But these three usually form the basis of a very strong authentication medium. So going back to that concept, there are three factors here. One is the knowledge of knowing the key. Possession, that is where you're holding them in your hand at that moment, which in our case, your certificates are going to be possessed. Your knowledge is going to be a secret key that is known by your client or your server. Inherence is something that is only possessed by that device or by that person. So, for example, for a person, it would be biometric scans, but maybe for a device, it is going to be a MAC address that is tied only to that device's hardware. So there are multiple forms of authentication that we can talk about: multi-factor authentication, host-based authentication, network access control, etc. And all of these, when implemented correctly, will give you a much more secure and robust way of talking to your devices and to your users. But I want to talk about two different styles of authentication, and I want to contrast them to give you a good example, a good view into what would be the constituents of a good authentication principle, and why we should be looking at them in much more detail than just on an overall level. So the first one I want to talk about is MTLS, or Mutual Transport Layer Security. And this is a certificate based authentication medium, and it is a long term and persistent form of authentication, wherein you're issuing certificates to both your client and your server, and each of them are going to be holding on to the certificates for an extended duration of time. Usually 365 days is not a long period of time. um, th- the second one I want to talk about is called JWT, or JSON Web Tokens. And these are much quicker to generate. However, they're also very easy to use, but they also come with their own pitfalls. And let us dive right in. So, mTLS, or Mutual Transport Layer Security, is at its base a certificate based authentication medium. It is a lot more secure when contrasted against your traditional username and password sort of combination. However, it is supposed to be used in concert with multiple different methods of authentication to give you the most secure browsing experience, or your even if you're doing device to device communication, even in those cases. So, what is TLS, and why are we using it the way we are? Let me just showcase a small lab at this point, and then we can talk about the details as we go along. Let me just switch screens. Just give me a second. Okay. So let me see. So what we have here are two very simple server and client um, application code that's written in Go. And if you look at the code, it's very straightforward. All we're doing is we're setting up a server and there's a handler that is going to be serving us on the port 9090. And Go is built from the ground up to be a very fast language to build your web applications on. So you have this function that does listening and serving, and it uses the TLS protocol directly out of the box. So all this is going to do is it is going to look for certificates, the server certificate as well as the server key, that are available on the device. And it is going to use these to ascertain that every time a client is coming is making a request, we serve those certificates to that client and let them know that this server is who we're supposed to be. On the other end of the spectrum, we have the client, who is also going to do something very similar. He is only going to make a request, and he's going to try and talk to this particular URL. So let's just spin up the instance. I'm just going to run CD into that particular thing. Sorry. Okay. So we have the server up and running. Now let's try and make our client talk to that server. So let's first access that particular place. Come back a step. Okay. So at its base, all this client is trying to do is trying to connect to the server, and what it wants to make sure that is happening is that when it opens a request to the server, it wants to make sure that the server has the certificates that were issued by some other third party. And why would we do that? Like, why do we want a certificate at all? Well, this is because of a attack vector called man in the middle. And the idea here being that there is always a possibility that the server that you're trying to connect to is not actually who you think it is. So you might want to speak to, let us say, google.com, But there could always be another server uh, that has registered itself with the same domain name, and you could accidentally connect to it without your knowledge, and obviously all of your conversation from that point forwards is compromised. So the entire idea behind certificate based authentication rests on the singular concept that there is a third party system or a body that has the ability to ascertain that the server and the client are who they are. So they will be issuing certain certificates that are signed by the private key of the server, and in the case of the client, the private key of the client. And there is the certificate issuing authority also provides their own key, and these two keys are used in conjunction with each other to ensure you always uh, have authenticity that is provided to your server and your client. So, in regular certificate-based authentication, the client is not required to provide any authentication of themselves. Their identity is not under question. However, in the case of your in today's world of multimodal cloud-based protocols and of the world where we are talking of device to device communication and APIs that are just talking to each other without anything in the middle, we we require a much more robust way to ensure that both bodies that are in the conversation are always authenticated, and every single time you make the request, you're still making sure that you're talking to the right device. So let me spin up the next instance, which is going to be this a very, very similar idea, but we're going to make sure that the server is also going to ask the uh, client to authenticate themselves. So in this case, you see that the server is using TLS, but it is not asking the client to do anything else outside of that. So let me just pull this down and go run server. In this situation, or in the second instance, in this case, we have the server asking the client to also provide some sort of authentication of themselves. So I think if you can look at this line, right, it is it is asking the client to authenticate themselves, and it is asking that the client should require and verify a certificate that is also going to be authenticated using the CA certificate file. So in the case of our lab instance, we've actually used a self-signed certificate, and this means that the certificate was generated right on this device and it was signed using OpenSSL. And I am the only body, or I am the only authority in this case. However, in the case of the internet, that is not going to fly. Obviously, we need our authentication to be done by somebody else, as in a trusted third party. And um, okay, let me move on. Let me just make sure that this is running as intended. So go run client cert. As you can see, the client that was also carrying its own certificates was able to go through. And in this case, you can see that the TLS has a client configuration of its own, and it has a root CA that is defined, and that is also pulling from a certificate pool that it is providing to the server when asked. However, if I were to run the previous version wherein the client is not providing any certificate of its own, yep, you will see that it is making a request that has a bad certificate. It's not able to go through. And in the case of the server, it says the TLS handshake error, the TLS was not able to go through because it is expecting a certificate to be provided from the other end where it received none. So let's talk about what we saw here. Well, first of all, so what is TLS? Well, TLS is Transport Layer Security, and it's a protocol that is trying to ensure that both the parties in our conversation, which is the client and the server, they're both using public key in cryptography. And usually, what we use for our certificates is either RSA or ECC. RSA being so our RSA is a version of a private public key combination, wherein we're trying to create enormously large factors of a prime number that cannot be guessed at by either by anybody outside the person that is creating the keys. So your private key is going to be generated on the device, and you're going to share a part of that key over your network with your server, and the server is also going to do the same thing. And over the course of a few mathematical functions, they arrive at a shared key that both of them can use, wherein the public key is used for encrypting and the private key is used for decrypting. And regardless of the network that they're sitting in, they're still going to be able to hold a conversation that is private only to them. And the only factor of leakage here is that they lose the key that they're using to communicate. If that is lost, then they lose what they've had so far. However, there are methods to ensure that this is not the end of the world. Um, so let us say you've lost your private key. You can simply rotate the key, or you can generate a new key, and you will still end up where you just started. You can continue the conversation as you already were. So, as is apparent, the important factor here is that the certificate that is being issued has to be issued from an authority that is trustable. So, how do we know that the certificate authority in both cases is somebody we actually trust? Well, in general, you have to ensure that the CA is using the certificate authority is using a public key infrastructure that is trustable and is managed in such a way that there is some sort of recognition. It's supposed to be a trusted third party organization, such as maybe WebTrust or ETSI. Additionally, you can also check if the CA offers quality customer service and technical support. You can also check if the CA's website itself is secure and encrypted for additional security. But all that aside, is is mTLS as safe as all that? Well, mTLS is sorry. mTLS is not secure on its own. It has been known to have a few failures in the past. For example, there was a case where I suppose the most famous one is called the Heartbleed attack, wherein the TLS authentication, the connection that was opened once, is kept alive using small packets that say, please keep it alive, or it says an OK message that says my length is 2 bytes, or so on and so forth. And when the client pings the server with this message, the server responds saying, okay, I will keep this connection alive for longer, because HTTP is a stateless protocol and it does not keep state. However, these messages can be used to keep the connection open and running. There was an overflow vulnerability wherein if the message was intercepted on the path, and instead of saying 2 bytes for a message, if it read something like 64 kilobytes, it would read back into the memory of the server, and the server would sometimes dump very interesting information back into the network completely unencrypted, because it is expecting it to be a very simple ping message, but it happens to uh, go back into the memory of the device itself. Okay, so that's about mTLS. Let me move on towards JWT. And okay, so let's talk about JWT and why it is um, important. On the other end of the spectrum, from our mTLS, which is a persistent-based authentication protocol, wherein we're trying to set up long-term authentication mediums. Where, for example, you are an employee at a company and you want to continue to use that network or that device for a long period of time, then mTLS is a very good authentication medium. Or within the confines of a data center, you have server racks that are connected physically to that they're tied down to that space. then mTLS is again a very good idea. But there are cases wherein you want much faster and much snappier responses, and you want to have a large flow of customers that you want to talk to. However, these are also not people that you would continue to have the conversation with for forever. I think a good example for this is let us say you have a patient that goes to a hospital. He is not going to continue to go there for he's not going to be there for days on end all over the year, but he will continue to go there at short bursts of interval. Like he'll probably be there once in a month or once in a few months. The information that the client, in our case the patient, his information is important. However, the server need not store all of his information, and the authentication protocol also has to make sure that it serves him at the fastest time possible, while also making sure that it is not losing its own performance. JWT is a good example for making this happen. So let me just show you a lab of how we can make this work. Let me just switch screens real quickly. Oops. Okay. So to break down the text, the code itself, this is a very simple application. All it is going to do is it is going to ask a user to log into our application, and the sign in function is going to give them the ability to use JWT as an authentication protocol medium. So let me show you the handlers, which is where the interesting stuff happens to be. And to understand very simply, we have a credential structure that is going to ask for a username and a password, and we have claims being an interesting thing that JWT carries in the as opposed to mTLS, which is only going to be used for very small pieces of information. For example, you're only going to pass on your public key or whatever HMAC address that you have generated. Instead of doing that, claims allows you to send any JSON key pair over your this thing as your authentication medium over a token JWT. So in our case, we're going to be using two pieces. One is going to be the username, and the second piece is going to tell you how long that JWT has been active for, or how long it is supposed to stay active for. So we're going to be sending the expiry date, expiry time, and the username over this. So let me just show you the sign-in function. Actually, let me show you the welcome function, because sign-in function also contains authentication, which in our case is not really required to be verbose. So let's leave that out. So what we're going to do as soon as somebody signs in, okay, let me just really quickly go through this as well. As you can see, as soon as somebody tries to sign in, what we're going to do is we are going to be decoding the JSON web token, the JSON file. I mean, the body of the JSON that they're going to send us, which we're expecting to be just the username and password. In this case, it's going to be plain text, but yeah, we're going to ensure that the password is as expected for the users that we have. And in our case, the users are just user one and user two, and the passwords are password one and password two. Again, this is a proof of concept, but bear with me. So as long as we find the expected username and password, we are going to be okay with this, and we're going to allow them to go to the next step. If it is not what that, if the username is not user one or user two, then we immediately tell them that's not what we expected. But moving forward, we are going to set claims on a JWT token saying that as soon as one has signed in, we are going to issue them a token that is going to expire 5 minutes from the period of issue. And in this case, you will see something interesting here. This signing method that says HS256. So here, I think is a good time to talk about two different modes of PKI, public key infrastructure. One is called symmetric keys, and the other is called asymmetric keys. So in a symmetric key, both your client as well as your server will use the same secret. So the expectation here is that they have shared the secret way before this process is happening, and they have both individually kept the secret in a vault or in a similarly secure environment where it is not prone to leakage. But clearly, the more number of if your private key is not being held at only one single location, then you're also like multiplying the chances that your key might leak. And in a server client protocol, in a server client architecture sort of setting, you have multiple clients, and with every single client being added to your list, you're only exponentially increasing the risk that you have faced with the same thing. And in our case, if you probably noticed in the very beginning, our JWT key is just something that says my secret key. This is obviously the worst way to do this, but it stands to the reason that if you are able to do this, your client is also going to store your key in a similarly insecure fashion. So HS256 it stands for HMAC, which is a signing it is a method for signing your JWT token, and this uses your a method of signing which is a symmetric key, and in this case both you as well as the client are going to be sharing the same key, which is terrible. So what is the other option? Well, you can use RSA, which we spoke about in the previous division. And RSA is an asymmetric type of key storage, and it allows you to use two different keys, and your public key and your public key is shared over your network, while your private key is held only by you. What are the other types of asymmetric encryption? Well, outside of RSA, you also have elliptic curve cryptography, and you have Diffie-Hellman. Elliptic curve cryptography, which is rather new to the scene, has been known to be much faster than RSA. So why would you use HMAC or in case where you already have RSA? Well, HMAC is much faster. It is more effective and more efficient. It is more prone to secure leaks. I mean, it is not as safe. However, it is RSA takes much longer to compute, and your therefore your response from your server on your web server is not going to be as fast as you expect it to be. But yeah, moving forward. So we're expecting your application to set a JSON web token that has your expiration date set on it. We are also claiming that the claims are going to look for your username, and once the username has been provided, it's also going to give it an expiry token. And your JWT is going to be signed using the HS256, where your secret is known both to your client as well as your user, your server. And finally, all of this information is going to be stored within a cookie that is available to your client. And as long as your client brings back this cookie containing this information, you're going to allow them to access the web page further. So this welcome page, as you can see here, it is going to expect a token, that's a cookie that called token. And as long as it contains the JWT string that we expected and it has the claims that we expect it to contain, then we're going to allow it to finally say, yes, hello there, Mr. So and so. So let's just run this really quickly. Let me just build this. Yeah, making sure that's the latest version. And we've run this. So it's up and running. Now let us try to access it. So for this instance, let me just show you using Postman so that we can see what's going on behind the scenes. Let me present that part. Okay. Okay. So all I'm doing here is I'm trying to sign in to my server that is being hosted locally, and I'm trying to hit the endpoint that's called sign in, and I'm sending it my username and password using this over plain text, which is terrible. But the idea here being that it is going to it is going to reply back to me using a JWT token that I can then use from this point onwards to authenticate myself. So let us say, for example, I were to not give it anything right now, and I will just try to hit the welcome post, the welcome endpoint, and it should say 401 unauthorized. I'm not allowed to access this endpoint. However, if I were to, there you go. So as you can see, it is responding back with a token value, and this is a JWT token, a JSON web token that contains information about the client, which is me. So let me see if I can break this down and show you what it's supposed to look like. Okay. Oh wait, before we move on, let me also show you that this is allowing us to access the web pages. There you go. So the endpoint welcome, which was here for to blocked off, is now accessible because we are able to authenticate ourselves, and we are going to the server with a cookie that contains the JWT that was issued to us beforehand. And the JWT is still valid because it has not been 5 minutes yet, and it contains some information about me, which says I'm user one, and the expiration time has not been reached yet, and three, it has not been tampered with. And how would we know this? Well, let me just break down the JWT token really quickly. So there is a website that is called jwt.io, and these folk do marvelous work for using JWT tokens. So if I were to paste my JWT token here, then you can see that the username is set to user1 and the expiration time is also set. So these are the two things that my server is using in order to try and verify that I am who I am. Further, the end of this token is going to contain a secret that we have used beforehand. I think the one that I showed you that just said my super secret. That is going to be used in conjunction with the rest of your token to ensure that nothing within the token has changed since the moment it has left the server or it has left the client. Meaning the issuing a body has power over has a unique method of signing it, and only the client that also has the same key is going to be able to decrypt it and then read it. In this case, if somebody were to mess with this, like let's say if I make this user 2 instead of 1, then immediately the signing part of this token also changes, which means when my server reads this token, it is going to know that I have changed the contents of the token somehow, and it immediately invalidates all of this. And this is how JWT allows you to have verbose communication and authentication over a network, wherein most of the data is being held by the client himself, and he's going to take it as a claim to your server whenever he requires it, instead of keeping it all on the server and therefore like slowing it down. JWT is a faster method to do so. But in both cases, you will have noticed that there are some pitfalls, and let us just talk about them really quickly. So, what is JWT? Is JWT completely safe? Well, even though we've said that the if somebody tampers with a JWT, it is going to be immediately noticeable. That is not true in case your secret has been leaked. If you're using symmetric keys and your key has been leaked somewhere on the internet, then there is a possibility that the uh, malicious actor can also replicate the same JWT token that you were supposed to have. They can also be used for replay attacks, wherein the JWT can be replayed or reused multiple times, allowing the malicious user to gain access to their resources without the need for authentication. Because in general, JWT assumes that authentication has already happened beforehand and it is only continuing a conversation. And finally, if your JWT is being generated without sufficient entropy, then there is a possibility that your token is also going to be untrustable. Well, is that the end? Can we not do anything better about it? Obviously, we can do better. Well, JWT tampering can be addressed using digital signatures, and these digital signatures have to be signed with appropriate techniques. And one technique that we talked about was the RSA 256 key, which is going to ensure that you're signing it with a public and private key pair that is secure and quite long. And RSA itself is also vulnerable to attacks if the key that you're using to sign is not sufficiently long enough. And I think the current standard is for 2048 bits of a key, which is highly secure. Obviously, we also talked about your key itself, which is going to have to be held in a secure storage space. If your clients have access to the key and they leak it somewhere, then you have to make sure that you're rotating your keys on time and you're able to stop the problem beforehand. And this is one thing that we already talked about. Replay attacks are going to be a thing if you're not going to have an expiration time set on your JWT. But that can also be addressed in two ways. One, you can have an expiration time, but the second one is using it as a one-time use restriction. So this method is extremely powerful because it is going to ensure that it is used exactly one single time. And the second time, you're going to have to completely generate a new token. And anybody who's trying to steal that token, they will have a much harder time of doing so. Finally, if you have insufficient entropy while generating your JWT, then you're going to have to use a much more secure random number generator, which is readily available. There are a lot of libraries that do the same business, and that should take care of the issue for you. Well, I think that brings us to the end of this session. Let me just quickly switch back. Seems like my computer has frozen.
Whoops.
Well, take it away.
Sure. Okay. Thanks so much for your talk, Ganga. This was a great way to conclude our monthly live streams for 2022. And thank you to our viewers who have stuck around for the whole session. I really hope you've learned something new today. This has been a ton of fun, and we cannot wait to see you again on the next live code in 2023. Until then, bye bye.
Thanks for having me.